Yeah, good evening, everyone. Now, now Matthias Peyer, who does now his PhD in software security, which sorry, I must start over. I'm a bit nervous today. So, I'm proud to present you Matthias Peyer, who currently works on his PhD in software security, and in a sub-theme of his is software defense, and within this sub-theme he works on a topic called string-oriented programming, where he does analyze how format string attacks can be used to attack programs. So give him a round of applause.
Thank you very much for the warm introduction. It kind of brought back memories to last year where I stumbled over the first couple of sentences. So let's just hope that this doesn't happen this time. Thanks. So to get to the topic, what is it all about? The motivation behind the work that I did here was that there are a lot of additional protection mechanisms out there, and they are used more and more in the wild. And the standard security configuration is changing for stock operating systems. So, and in addition to that, additional hardware mechanisms are being developed that stop all our traditional exploits. And we need to find new ways to exploit these running systems to get access to the code and to inject our own data. So we have hardware mechanisms like data execution prevention that is out there, that's standard, that's usually enabled right now, and it's out there and used, and this makes many of the traditional exploits impossible, or a lot harder at least. And we also see, you don't actually have to read this table, but this is the comparison of the Ubuntu security features from the old versions, for all the old versions. And basically you see that they started off with only a few little bits and pieces enabled, and the current version has like a ton of additional security features out there that protect from many of our standard and well-proven exploits. So what can we do about that? What part of it has been overlooked? Well, format strings had a big hype in around 2000 and something, but nowadays they are a bit overlooked. On the other hand, there's a drawback that they are very hard to construct, especially with a couple of these new protection mechanisms that are out there. So we need to define a way how we can deterministically exploit these format string bugs and get access to the machine in the end. And that's what this talk is all about. If we look at the attack model that we assume, we see that an attacker with some restricted privileges on a machine wants to escalate his privileges up to a higher level. So for example, we have a local user that wants to escalate his or her privileges to a system user account, or we have a remote user without any user capabilities that wants to force user capabilities on top of that. So we also assume we live in an open source world. This has many advantages, but one of the other of the downsides is that the attacker knows the source code, and if we are using a stock image, like for example Ubuntu server, the attacker also knows the exact binary and can replay the exact same scenario that is used on the server at home in his little playground. So we have to assume that the attacker knows all these little things. On the other hand, we define a successful attack to be if an attacker is able to redirect the control flow at one point in time to an alternate location by injected data or injected code. And we also require the attacker to execute either inject the code that is now part of the runtime image, or alternate data that is used for existing code. So the outline of the talk looks a bit like this. First, I'm going to talk to you about the existing attack vectors that are out there, the protection mechanisms that are used to combat these techniques. Then I'm going to introduce string-oriented programming, show you a little demo or two, if time permits, and in the end conclude. And if the demo works, as we've seen up with the in Saal 1 with the telecom guys. So the first of the attack vectors that we all got very used to and we all loved was code injection, which is one of the very nice and simple exploit that inject additional code into the runtime image of an application through some attack vector. Maybe we can use a buffer overflow to inject code into the runtime image, but the code is injected as data. So the processor will just execute that given data as new code, and in the end, the attacker will have control over the application. So if we have this little example program, we have a nice little buffer on the stack, and we execute our little string copy function. The buffer, of course, is limited, and in the end, we will be able to overwrite some stack data with that. For this example, we assume no protection mechanisms as have been around in the late 90s and early 2000s. The stack looks a little bit like this. We have our stack frame from the bottom. Then we have the first argument to our little function, a saved return address, a base pointer, and our little temporary array on the stack. So we start to copy our user input down from that pointer, and we will end up with something that looks like this. We have some nice little knob slide and exploit code that we injected through that data buffer, and we override the return address to point back to the beginning of the buffer. And in the end, we can get control over the application like that, because we redirect the control flow, we injected new code, and in the end, we execute arbitrary code that is controlled by the attacker. Well, but things have changed since then. Modern hardware and operating systems separate data and code. So on a page-level granularity, the operating system can enforce that it's either data or code that is on that memory page. And if it's data, and the attacker writes his nice code into that data page and wants to execute it by overwriting the return instruction pointer, the processor will raise an exception and stop the program because it is not allowed to execute. Due to this additional hardware, code injection is no longer feasible because the protection mechanisms ensure that a page is either writable or executable, but never both. On the other hand, there are some limitations. If we have a JIT program, like a Java virtual machine or things like that, they have a couple of pages around in memory where they place dynamically generated code. So we might still be able to get lucky with these old school exploits once in a while if the circumstances are right. So we already heard a little bit about the different protection mechanisms, but let's just look at the three most dominant protection mechanisms that are out there that make our lives a little bit harder. So the first protection mechanism is data execution prevention, called DEP, or exec shield on Linux systems. This protection mechanism enforces the executable bit that the hardware provides on a page-level granularity. And if a page is not executable, then code on that page will not be executed by the processor. This limits all our code injection exploits if it is set up correctly. So if this is enabled, data execution prevention, we can no longer use code injection techniques to get control of the application. The next protection mechanism is address-based layout randomization. Address-based layout randomization is a probabilistic protection mechanism that is also enabled by default on current kernels. And ASLR enforces that all memory addresses on the heap, on the stack, and for all libraries are dynamically shuffled around and randomized. This leads to the fact that if you think back to the code injection example or the code injection exploit, that we can no longer redirect the return instruction pointer to the beginning of the buffer because we have no idea where this buffer is located in memory. But the current implementation in Linux uses a static application where some part of the application still is located at a fixed address due to some optimization issues. And that's what we are going to use for that. And the last, but nevertheless still important, protection mechanism that I'm going to talk about is ProPolice, which is used in more current versions of GCC and so on. ProPolice adds additional canaries. A canary is a little bird that miners used in the old times to take down into the mine. And if the bird died, the miners knew that, well, the air is getting thin and we better should get out of here. The same idea applies to canaries on the stack. The compiler places secret hidden values in specific locations on the stack and checks these in specific intervals if they are still the same. If there's been a buffer overflow, the canary values will change. The program will detect that and terminate itself because of the buffer overflow that happened. So, well, if we combine these mechanisms, they make our life a lot harder. So let's look at what other attack mechanisms are out there that can help us in one way or another. We already know that code injection is no longer possible, so we have to move to a new attack form. And the new attack form no longer injects code or new code into the process image, but re-executes the already existing code with new data. So we search for specific code sequences, stitch them together, and just use a data-based approach to execute arbitrary commands. The idea is that we go one level higher. We no longer inject code directly, but we take a different approach. We see the program as a big interpreter that runs specific commands on top of it. So we just exploit the existing code sequences, reorder them, and due to the database approach that we have, we can execute arbitrary instructions in the end, and also inject code then. Return-oriented programming is one of these data-based attack forms that prepares a set of stack frames on top of each other with specific return instructions or return directions to code sequences in the program that are available. So if we have the same sample program from before, we once again have the stack frame, we use our buffer overflow, but we assume that data execution prevention is enabled, so we cannot inject code into onto the stack and execute it there, so we have to take a different approach. We once again copy the input, and we now don't care about what is in the temporary array at all. But we prepare a set of return addresses to point to a gadget catalog that we pre-identified based on existing code. Does it get away? Yes. So we search the application for nice instruction sequences that help us, that always end with a return instruction. So we then implement some kind of a stack machine on a stack with additional stack frames. You can see off the return address as an indirect control flow transfer to a new catalog, and the data is then used by these instructions in the catalog. And if this gadget ends or completes, we execute the next gadget. So this sounds like a very nice idea, but what are the drawbacks? If we use such an exploit, we still have the problem with address-based layout randomization because we don't know where to place the data and what we can do with that. And we also have a problem with ProPolice, with the stack canaries, because we just overwrite them, and we are not able to execute the first indirect control flow transfer that gives us the control over the application. So we have to escalate a little bit further. We have to refine our idea a bit more. And that's where jump-oriented programming comes in. Jump-oriented programming abstracts the idea from return-oriented programming to use data as an additional attack form, and moves from return instructions to any indirect control flow instructions. So any data region in the application that we control can be used as a scratch space to set up such an interpreter. Let's look at it. We have a scratch space at some static address that we control with a set of gadget addresses and data that we consume in this interpreter. So these gadget addresses point to the gadgets in our catalog. They are executed one after another, and the indirect jump transfer, control transfer at the end, always redirects the control flow to the big dispatcher. And the dispatcher moves from one entry in the scratch space to the next entry and executes all our gadgets one after another. Using these two abstract approaches, we can basically construct any code that is executed. So we can chain a set of library commands, for example. We can mmap a memory page. We can execute a string copy using the same approach that copies our exploit data into the newly allocated memory page, and we can then add a control flow transfer to that memory page and in the end execute our injected code again. But we first use this data-oriented approach to set up the scene for the following attack. So, well, what's the problem of jump-oriented programming? Once again, we have ASLR in there. If we don't control the heap, we don't know the addresses on the heap, we cannot get around these randomization problems that we examine. We also have the problem of propolis, once again, if we have some buffers on the stack and we get into trouble with the canaries. So we have to get around that as well. How can we do that? Well, maybe format strings will come to the rescue. Format string bug basically exploits the fact that a format string, well, let me tell you first what a format string is. A format string is a special string that is allowed to contain specific tokens that are interpreted in a special way, in a very general form. So you all, I assume that you all know the printf command. The printf command has a special string as a first argument, and this string specifies how many arguments on the stack will be consumed by the string that is printed. If a user can control this first string, he can basically place arbitrary special tokens in that string that read from the stack and also write to the stack if he used the %n token. So the %n token is a very special feature that comes from very old Unix versions that reverse the input and basically results in a random memory write. So we now redirect the input, and we no longer consume values from the stack, but we write to a specific location somewhere in memory, and we can control that location. So if the string is on the stack, we can also use the same string to store pointers and basically randomly write any data somewhere to memory if we construct the string carefully. So we want to write coffee babe to 0x41414141 and construct a format string like that with 2 half-word writes. The printf command consumes the first format string. The first 8 bytes of this format string are the 2 half-word addresses. The first time the AAA address, and the second time the AAAC address. These 2 half-word pointers are then used in the exploit itself. Then we just print a specific number of bytes to the terminal. In this case, we write 0x coffee minus the 8 bytes that we already wrote to the terminal, and we then use the sixth parameter. We assume that the string buffer that we control is on is 6 words up on the stack. Then we use the first pointer in there to write the number of already printed bytes to the given pointer, because %n can be used to write the number of written bytes to the terminal at that point in time to the given pointer. So we just write the OX coffee part, the first 2 bytes, to that given address. In the old days, these things were used for pretty printers, where you had a specific column width, and maybe you printed a string from a database or something like that, and you didn't know how long that string was, and you didn't want to call that expensive string length function. So you just stored a pointer, you just added a pointer somewhere that the %n then updated with the amount of already printed characters. And this way, it was very convenient to find these things or to use these things, but they're also a huge security problem that can be used up until today. So these random writes that we have can then be used to redirect the control flow or to prepare and inject malicious data. Basically, if you want to know more about the basic format string attacks, this is only a short overview that I can give here, but if you want to know more about basic format string exploits, you should watch the Black Hat talk from this year, where they talked about new format string attacks that use the similar approaches with these parameters. And they go into great detail about how to construct these strings. But still, it's kind of very cumbersome to come up with these strings. And to start with, it's very hard to get around ASLR, data execution prevention, and pro-police things if you overwrite the specific parts in memory. So let me now come to a generic form to exploit this format string exploit that relies on many of the attack vectors that I presented to you. String-oriented programming is the approach to execute arbitrary code through given data. What we need to construct such an exploit is a format string bug in an application and an attacker-controlled buffer somewhere on the stack. It doesn't matter where on the stack it is, we only need to know the offset from the printf function to that buffer on the stack. What we don't need to execute such an exploit is a buffer overflow, executable memory regions, or any other fancy things. When we use string-oriented programming, we build on the attacks of return-oriented programming and jump-oriented programming. And we also use some of these available gadgets in the application to then execute nice code sequences. With string-oriented programming, we can also patch and resolve addresses. For example, if you want to call a library function that is not imported in the current application, we can just resolve this location using some nice little gadgets that's usually available in the application. I told you before about the ASLR, address space randomization implementation in Linux, and they use a weak form of ASLR out of optimization issues. To randomly place the application somewhere in memory, you actually need to generate position-independent code when you compile a program. But the application is usually not so dynamic, so you have to place it always at the same location. And that's how we can come to our gadgets. We use the fixed application, search for our gadgets, and then also use static regions in the application to construct our data flow in there. So for example, if the application calls any library functions, we have things like a global offset table or a procedural linkage table that is used by the linker when the application is loaded to resolve connections to auto-shared libraries. And we can use these available offsets to our for our needs. So if we want to resolve a hidden function, we just search for a GOT slot that contains the pointer to that given function. If we want to resolve the pointer to a hidden function, the location of a hidden function somewhere in memory, if you want to break ASLR, we take the function that is used from the same library in the application, we read the pointer using a random read, and then we just add the offset between the original imported function and the function that we want to execute to that GOT slot, and therefore can resolve the given entry. So we assumed that the attacker has access to the binary, so the attacker can just disassemble the library and check the offsets between the locations. If we have one pointer into the library, we can resolve any other function in that same library and just add and adjust the offset in the end. So we can call any hidden function, for example, a nice system function, without any loader support. So I now want to go through the steps of breaking all the different protection mechanisms one after the other, and therefore we have this little running example. We have a buffer on the stack. The user or the programmer added a length check that checks for the given length on the stack. If the input buffer is longer, then we fail. Then we copy it to the local buffer and just print that buffer. The attacker controls the string and can inject arbitrary data in there. So how does it look like? What can we do with that? First of all, if we don't have any protection at all, then all addresses are known. We don't have any execution protection, no stack protection, and nothing at all. So what we do is, here we have the three stack frames, the main frame, the foo frame, and from the foo frame we call the printf function. If we look into that, we have the buffer on the stack, we have some unused bytes that are left out of for alignment reasons, we have our EBP and EIP in the end. So what we do is we just inject a string with a random write and some exploit code, because we have no execution prevention, so we can execute the data as code on the stack. The random write at the beginning of the format string will overwrite the saved EIP in the end in the printf data to redirect it to the format string, and it will then execute our nice exploit in the buffer that we placed. But unfortunately, things are not that easy, so we add data execution prevention. So data execution prevention prevents code injection. So we have to rely on return-oriented programming and jump-oriented programming instead, and go back to that. So fortunately for us, any program, as small as it is, even if it's just a one-liner, does not only consist of the one line of code that you add, but if you use the GNU C compiler, it will add a couple of functions that actually set up the application, call the loader, and do many different things, and also initialize the libc and things like that. And as part of that setup code that's always available in any compiled application, we have a nice frame lift gadget that we look at in a bit more detail. This frame lift gadget can be used to add OX1C bytes to the stack and gives us control over the EBX, ESE, EDI, and EBP registers. So using this little gadget that we have available at a static location in every single application, we can control 4 registers and we can adjust the ESP. With that little gadget, we can do some nice things, like once again we have our 3 frames, and we look again at the foo frame in the middle, and we place our random write and our stack invocation frames in these in our buffer. So we then override the return instruction pointer using the random write to the frame lift gadget. The frame lift gadget pops the 44 bytes from the stack, ends up in our buffer that we control, and we now can execute the stack invocation frames that are available in the buffer. Well, this is pretty nice, but there are other protection mechanisms out there. So what happens if you use Propolis? Propolis uses and enforces these stack canaries. So we once again have our 3 stack invocation frames. We look at them in a little bit more detail. The GCC implementation of Propolis uses the stack canary at the end of the buffer to check for a buffer overrun and copies the arguments on, at specific locations in the stack to ensure that the following functions can always use the correct value of the parameter. But well, if we reuse the same mechanism, we can actually keep the canaries intact and just reuse the same random write to redirect control to the frame lift gadget, and we will end up in the stack again, in our stack buffer again, where we can then use arbitrary stack invocation frames. The fun thing is, once you get around the Propolis protection, you no longer have to worry about these protections because you control the control flow and all the following control flow transfers. So as soon as you're able to redirect the control flow to your locations, you can execute arbitrary stuff in arbitrary stack frames, and the game is lost for the defense guy. So this is pretty nice and sweet, but what changes if we add ASLR, address space layout randomization, to the picture? So if you combine address space layout randomization, data execution prevention, and Propolis. So if we combine all these defenses, we have to rely on the already existing code and on the static locations that we know about. We also have a set of imported functions in the application in the procedure linkage table and some symbols in the global offset table that we can reuse for our purposes. So in the end, we can just use random byte writes to adjust these global offset table entries and redirect the control flow in a specific way, and then rely on the different functions that we set up that will be called in, at other places in the application. And we can then combine stack invocation frames that we place somewhere, plus the indirect call and jump gadgets. So to make it a bit easier, we just look at this little program here where we once again have a buffer of around 1 kilobyte on the stack, which is protected by Propolis, so we cannot misuse the string copy function, because otherwise the program will fault. We will then have a printf and some other function in the end. We don't really care about it as long as it is imported through some external library. It could be any function, basically, for this example. So if we zoom into the application, at the point where the printf is executed, we see a picture that looks a little bit like this. We have the static part of the application on the left-hand side, where we have a couple of pages that are mapped readable and executable. That's the init section, the PLT section, the text section, and the finish section that is available in the application itself. In the PLT section, we have the 2 link calls, system at PLT and putS at PLT. And in the text section, at one point in time, we have our little and nice lift ESP gadget. At the point in time when we execute our format string bug, the printf function, the stack check file function from Propolis, and the putS function all point somewhere into the libc code that is somewhere in memory at some randomized location. The libc, all other libraries, the heap, and the stack are all at random locations, and we want to get around that. So let's just zoom into the stack frame. It looks pretty similar than before. but now it's all at a random location, plus the canaries, plus the data execution prevention. So what do? We no longer need just one memory write, but we need, for this simple example, we need 3 random memory writes, plus a set of stack invocation frames. So our 3 random writes help us to get control over the application. First of all, we want to get around ASLR and propolis. So we place some data in the read-writable section that contains the global offset table, the procedural linkage table, and so on. And we just overwrite these 2 functions. Nobody told us that we actually have to rely, or that these little things are pointers. We can also reuse them as just some scratch space where we can add any data. So we place the nice string /bin sh into some read-writable section that we can control. We now have, so in system languages, you don't have a type checker. That's why we can just reuse any memory regions for our own purposes. So we now have our nice string in there. You also see that we have a null byte in there. We can easily write null bytes with these format string bugs, because we can just control it. The null byte doesn't have to be part of the format string. We can just write 0 bytes and then write the 0 somewhere to a given location. So the second, these are the first 2 writes. Bin shell are 8 bytes long. The third byte redirects one of the imported functions. We no longer can just easily redirect the stack, the return instruction pointer on the stack, but we have to override a specific function that is called in the control flow of the application after our exploit takes place. In our example that we just looked at, the putS function is executed right after the return from the printf. So we just override the putS slot in the global offset table to point to the lift ESP gadget. So when we now execute the putS, or when the application executes the putS function, it gets redirected to the lift ESP gadget, which in turn will pop a specific amount of bytes from the stack, which will end up in our buffer that we control, and in the end we can just execute our special stack invocation frames and use return-oriented programming for that. If we would like to use jump-oriented programming, we could use a similar approach where we redirect it through the return address to some jump-oriented programming space. So to make you believe that this actually works, I have this little program here, the format string bug with all these things. We can add a parameter in the end. This time it's ASDF. It prints out some debug values. Main is located here, foo is here, argv is here, and we have other values in there. And here we print ASDF, and the putS function prints out that a nice redirect is possible. And we return safely. Let's execute it again. You see here that, oh, these things are actually randomized. I'm not joking. You see all these things, some of these things change. But other things like foo, all functions that are part of the actual application remain the same because they are static. So let's just execute our format string. We have the same program. We use our little format string construct Python script. We place stack invocation frames on the stack in the buffer, and we prepend our generated format string with some garbage data or with some additional data. Here we have a coffee babe. It's always good to have one of these coffee babes around. Then we add our stack invocation frame, where we have just one frame where we use the puts, the system function that we imported, and we give the pointer to the global offset table, or the part of the global offset table where we placed our string in. We then tell our format string constructor that, well, we have to, the buffer that we control is 12 words above the printf function, so that we can adjust the parameter accordingly. And we write 3 values. To this value, which is the same as this value here, we write the first part of /bin shell, and to the other 4 bytes here, at the later point, we write the second part of bin bash. And we also override the puts function, which happens to be at this location in the global offset table, with the nice value of our frame left gadget. So if we execute this, it runs, and we end up in a shell. And if we are an external user, we now have control over the application. And we go back and we fault. So these things can nicely be used as a chain of escalation to break all the different exploit mechanisms. We got around ASLR, we got around data execution prevention, and we got around ProPolice, all in one go, with one simple little format string. You can also look at the format string. It's 127 bytes long. Let's just look at it without that. So it's just 127 bytes long. There are the pointers that we use in the beginning. Then we generate the random writes, a couple of half words that we write, and in the end, we win. So let's switch back to the presentation. You all believe me that these things work. The script is fairly easy. It will be on the web page. You can look at it, and you can generate your own format string. And it comes with some additional playing material as well that you can use to get around it. So, what did we learn? First of all, string-oriented programming relies on a format string exploit and extends data-oriented programming, like return-oriented programming, jump-oriented programming. We now see the application as an interpreter for our data that we add. And this interpreter can be used to execute arbitrary code. We can easily circumvent data execution prevention using one of these data-oriented techniques. And we can get around ProPolice by using the format string exploits to exactly just override the values that we want to change. And we can reconstruct any pointer and circumvent ASLR using these global offset table and procedural linkage table tricks that I've shown you a bit. So the format string bugs that we see here can result in a complete compromise of the application and full control for the attacker. So to protect against string-oriented programming, we would need to go one level higher and maybe use virtualization techniques or things like that. And we also have to look at the complete tool chain where these format string bugs actually come in. So with this, I would like to thank you for your attention, and I'm happy to take your questions. Yes?
I have actually 2 questions. First of all, well, it seems to heavily rely on format string bugs. And, well, if the format strings are implemented correctly, then this whole thing doesn't work.
Well, if your program doesn't have a buffer overflow, you have no exploit as well, right?
Yeah, of course. And the second question is, you mentioned the gadgets that the GCC leaves in the program, but wouldn't it be basically possible to kind of externalize these gadgets because they are needed at initialization of the program only, and maybe if one adds some code to Linux program execution, then these gadgets wouldn't be visible to the program itself.
Well, in theory, yes, but it's hard to do. Part of the gadgets also come from the area where you can have constructors and deconstructors, and they're just in there by default. If your program uses them, you actually have to add them to the application. You could just strip them if your program doesn't use it. But GCC just uses a small set of these start files, as they are called, and adds them by default, even if your program doesn't use it. You could change the Linux kernel in one way or another, but then you would basically just move the loader into the kernel. And the loader is a huge mess of code that you don't really want to look at.
Okay.
Did that answer your question? Okay, thanks.
Okay, I have one small inquiry from IRC. Angstrom asks what Black Hat talk you were referring to earlier regarding format string exploits. At which Black Hat probably would be enough.
The 2011, this year's Black Hat.
Okay, because apparently
it's extended format string exploits by Blitch, I think.
Okay.
I would have to look it up.
Okay.
I can put it on the slides when I put them on the web page.
Yeah, apparently he looked at 2011, didn't find anything. But okay, if you say it's there, it's probably there. And one that's begging for Holy War, Joey A1 from IRC asks, according to Microsoft, the person sign N type has been disabled since 2005, and he wants to know why it's still available on Linux.
Because a lot of old software is still using it. There are guards out there that are implemented in newer versions, but basically libc is a huge mess in one way, where you can just disable these guards at runtime with some... In your format string exploits, you can disable the guards that should check for the format string exploit. So that's just an additional nice thing. It's out there. But I didn't add that to the slides because it would get too complicated. But the %n is still out there, and you can still use it. If you have a format string that you can control, so if you have a printf where the attacker can control the format string, even if these protections are enabled, you can get around them pretty easily. Okay. Are there any other questions?
So, I don't see any other questions here in the room. So, thank you, Matthias. It was a very interesting talk. Yeah.
Thank you.